The topic is interesting. I'm excited to be speaking about this because, well, it's something that we get asked about so often.
I know, right?
Okay.
Yeah.
Yeah.
All right, let's get underway. I can see people are still trickling in, but they can join us as we get underway. So thank you everybody for joining us tonight for this webinar on high availability in Postgres, specifically for Oracle DBAs. Some of us in this webinar come from a long Oracle background. And we thought it might be fun to run this session specifically for people from that background on Postgres. So just before we get underway and before we make the introductions, just a few housekeeping rules. So if English is not your native language, then just be aware that translations and closed captions are available. Just click at the bottom of your screen and select what you want to translate to, and you'll be able to see captions at the bottom of your screen. If you do have any questions as we go along, I do encourage you to put them in the Q&A straight away. Please don't wait until the end because as Umair presents the session, I'll be answering those questions as we go. Don't leave them till the end just because we might run out of time. We've got a very interesting session today with a lot of content. So I'd rather you get your answers earlier rather than later. And finally, we always get asked, are you going to get access to the recording? The answer is inevitably yes, you will. It's going to be provided in an email after the webinar is complete. Please do give us some time because it can take a while to generate and upload to YouTube, etc., but you're definitely going to get a link by tomorrow. So with that said, my name is Alex. I hope I bear some resemblance to that very nice marketing image that you can see on screen right now. I'm here from DBVisit Software speaking to you today. We are experts in Oracle database disaster recovery and have been for over 20 years now. You can see all that text on screen. I don't need to go through it. The point is, we've been doing this for a long time. We know what we're doing, how important database disaster recovery are, and how important it is to think about these things before something goes wrong. So I'm joined today by the wonderful gentleman Umair Shahid from Stormatics. He's going to be presenting today's session. Umair is a veteran expert in the PostgreSQL world, and we work a lot together. This isn't our first rodeo. I always enjoy very much presenting with Umair. We have good conversations as we go along and a little bit of fun as well. So I hope that will be useful to you. The agenda today is, look, what is high availability on Postgres? You know, those of us coming from the Oracle world like I am, you know, the concepts of high availability and disaster recovery are pretty well established, and there are kind of significant differences between the two. But in the PostgreSQL world, it's all a little bit different. So Umair is going to tell us all about it. He's going to tell us different ways that you can approach it. What are the important differences between replication methods and how we approach the solution to the problem in general. So as I said, Umair is going to be presenting the majority of the session today. If you have any questions and answers, please ask them in the chat as soon as you can. And with that, I'll hand over to Umair.
Thank you, Alex. I'm going to try and share my screen in one attempt. Here you go. Alex, please confirm when you see it.
Yep, you're all good. I think we're good to go.
All right. Well, thank you for having me on today, Alex, and thank you for that intro. High availability is a very interesting topic in databases in general, and particularly for anybody who's doing some kind of cross-linking between Oracle expertise and Postgres. Both of them are databases, but the technologies are somewhat different, and some of the terminologies might be a little different as well. So we figured that let's tackle that concept that is extremely important in any production database, and talk about how it works in Postgres. So when we talk about high availability, what exactly we mean. Essentially, what we mean is that our database should remain operational despite failures of hardware or software. So that's the key over there. It doesn't matter if there is any kind of failure, if a data center goes down, if a connection goes down, if the network fails, the database crashes, the host OS crashes, whatever happens, high availability is all about remaining operational despite everything. It is designed to minimize downtime. Critical applications, mission critical production applications cannot afford any downtime. And high availability is especially important for applications that require 24/7 availability. The way it is measured is what is called nines of availability. And let's take a moment to understand what nines of availability mean. If it is 90% available, that is 1/9 of availability. So because, well, you see 1/9 over here, it's 90% available. 2 nines is 99%, 3 nines is 99.9, all the way up to 5 nines, it's 99.999%. And with every 9 that you add, basically you increase availability by 1 order of magnitude. So with 1/9 of availability, 90% means that in a typical year, which is 365.3 days, you have a downtime of 36.53 days, which is 10% of downtime. Go one step higher with 2 nines of availability. You move 1 decimal place and you come down to 3.65 days, so 1 order of magnitude. And so on and so forth till you reach 5 nines of availability, which translates into 5.26 minutes of downtime every year or in a given year. Now, keep in mind, with every 9 that you're adding, you are adding a magnitude, 1 order of magnitude of availability. And correspondingly, the complexity of achieving that availability also increases exponentially. So going from 1/9 to 2 nines requires an order of magnitude of additional effort and so on and so forth. Achieving 5 nines is an extremely difficult task, which requires a lot of effort and complex architecture. You will notice that there is no section in here of 0 minutes of downtime per year because, well, if somebody claims that they can be 100% available, I'd like to have a conversation with them and understand what kind of magic they're running.
Exactly. That would be a lot of fun, right? Like it's one thing to read about these things, but it's another to actually implement them. And anyone who's actually tried this will tell you that it's the law of diminishing returns. Every time you want to go up an order of magnitude for availability, the complexity of the solution increases. So anybody who says that they can have what would it be, Umair? It would be 30 seconds of downtime per year, right? It would be about 30 seconds of downtime. Yeah, I'd like to have a word with them as well.
Yeah. So yeah, I don't know. We have gone to up to 5 nines of availability. I honestly don't know how to go to 6. But maybe technology is going to advance in our lifetime to get to that stage.
We're working on it, Umair. We're working on it.
Yep. Okay, so that's nines of availability. Now here's another frequent question that we get, right? The database resides on the cloud and the cloud is always available. So, well, that is 100% availability, right? Well, you would be wrong in that as well. Here is, an excerpt from the SLA that AWS provides. In a multi-availability zone database instance and a multi-availability zone database cluster, what AWS promises is commercially reasonable efforts to maintain an uptime of 3.5 nines. So if you see over here, the best that they commit to or they write about is 3.5 nines. And what they say is that they want to remain between 2 nines and 3.5 nines. That's the best that they commit to. And if they fall, let me rephrase that. If they fall below 3.5 nines, but remain above 2 nines is when they say that they will give a 10% service credit. So 3.5 nines is what they are committing to over here. What does 3.5 nines actually mean? It is 4.38 hours of downtime per year, and that is 22 minutes of downtime every single month. Amazon says that that's the best that they can offer. And Amazon is the most popular cloud provider and database as a service provider out there. What do you do if you want to be better? If you cannot afford 22 minutes of downtime every single month? Well, you have to have clustering, you have to have better reliability, and you have to have redundancy in place. Now, what is clustering? Now, remember what we're talking about is going to be in the context of Postgres. Many of these concepts and these terminologies are going to have an overlap between Oracle and Postgres. Essentially, an Oracle cluster and Postgres cluster mean something very, very similar. There are going to be some subtle differences, which I would try and point out. And I'm sure that Alex is going to keep me honest as I try and do that.
Always.
Now, so the way clustering is implemented in Postgres is that there are multiple database servers that work together to give the appearance of a single server working. So to the application that is interacting with the database, it appears like a single server, and internally that cluster manages whatever redundancy needs to be managed. The application communicates to the primary server, which you can see at the top over here, and the data gets replicated to multiple standbys, which you see at the bottom over here, standby number 1 and standby number 2. So to the application, it only sees a single server, and that is what it is writing to and reading from. And there is redundancy within the cluster. That's how clustering is implemented. Now, how replication works in Postgres, if we go to the previous slide and see that there is data flowing from the primary node over here to the standbys, how this replication is implemented in Postgres is through the concept of what is called write-ahead logs, or WAL. So basically, every single transaction that takes place inside of Postgres is written to a log file, is recorded on disk in the form of a log, and it is the write-ahead logs that are committed to disk that make up the data or make up the database. And it is these same logs that are transferred or replicated over to the standbys, replaying of which helps them maintain the similar data as in the primary. So in this case, application writes to the primary. I'm not actually sure which kind of annotation is already there, but yeah, okay, there you go. So the application writes to the primary over here, and the primary creates these WAL records that are stored on disk. Because we have set up a cluster, the primary has a WAL sender defined. And this WAL sender is designed to send off these WAL records off to the subscribers of replication. So this node right here is the publisher, and these two nodes right here are the subscribers. So the WAL sender sends off all of the WAL records to the subscribers. So one record goes here, one record goes here, and these records are received by these subscribers in a WAL receiver. And this WAL receiver replays all of the logs onto disk, and that is how these standbys get the data. So this is physical streaming replication, and this is how physical streaming replication works in Postgres.
So
moving forward.
yeah, just before we
And
move on, Umair, just a very quick comment as you know, for those of us coming from an Oracle background. So this is very similar to, in Oracle, the concept of shipping archive logs. I can see we already have a question about what is WAL. So WAL stands for write ahead log. And write ahead log is just a type of log file, essentially. It's a physical file on disk. It's replicated over to the standby and can be restored onto it. Now, within the diagram that Umair is showing right now, there are actually two different types of replication methods. In Postgres, you can have something called streaming replication, which means that the standby is actually being replicated to almost in real time. And you can have something called WAL archive log replication, which really is quite similar to what we would call archive log replication on Oracle. But regardless of which of those two methods is used, they will depend on WAL records being written and then sent. By the way, we will go into more detail on this as we go on.
Yep. So yeah, write-ahead logs form the basis of all kinds of replication as well as high availability in Postgres. So they are the central to the entire theme. Some definitions, I'm sure that most of our audience already knows this stuff, but just to give a quick recap, recovery time objective, something very important in both high availability and disaster recovery is how much downtime you can afford, how quickly you need to be able to recover from an outage. Recovery point objective is the kind of tolerance you might have for data loss. So depending on the RTO and RPO that your organization has, you design the cluster accordingly. Now, ideally, our customers tell us that they need both RTO and RPO to be zero or as close to zero as possible. But of course, the closer you get to zero, the more complicated the infrastructure becomes, the more sophisticated the architecture becomes, and the more expensive it becomes to maintain RTO and RPO of close to zero. So we have to balance that and decide what is acceptable. Failover is an unplanned process where something happens to the primary node and a standby has to take over. It's an emergency operation. It's one way. It's not reversible, or it is designed not to be reversible, and it takes place if there is some kind of an outage. On the other hand, a switchover is a planned takeover of a standby from the primary node. It could be for maintenance purposes, it could be for testing purposes, whatever it may be, but switchover is planned and controlled. As we establish these definitions, just a visual representation of what a failover looks like. So step one over here, it shows that, let me see, step one right here, the primary has gone down for whatever reason. Maybe there has been a system crash, maybe the network connectivity has gone down, or whatever reason, and the cluster detects that the primary is no longer available. What it does is that it removes the primary from the cluster. It promotes one of the standbys to become the new primary, and it sets up the other standby to become, well, the primary standby for the cluster. And then after this entire procedure has taken place, you can add a new node over here to act as the new standby. Or if you were able to recover this primary somehow, you can have this primary come and join the cluster as a new standby. This entire process of the primary going down, a standby taking over, and the other standby subscribing to what is now the new primary over here, this whole operation is called failover. When it happens without human intervention, when it happens automatically, it is called auto-failover. Okay. Moving on. Again, a few concepts to clarify within the realm of Postgres. The standby nodes could be warm or hot standby and warm standby. The difference is with the warm standby, the standby node is ready to get promoted to the primary in case a failover is required. While it is in standby, it cannot accept any connections, nor can it process any queries. It is simply receiving logs, the write-ahead logs from the primary and replaying them on the host to make sure that it is ready to take over and that it has all of the data that is required to become the primary. A warm standby is used for disaster recovery purposes. In case disaster strikes and you need to recover, you can recover from the warm standby very quickly with an RTO that is low and hopefully an RPO that is low as well. Hot standby, on the other hand, is not just receiving all of those write-ahead logs and replaying them on it to make sure that the data is up to date. It is also ready to accept connections and process queries. Now, these queries are read-only, and it is used essentially for load balancing purposes. But along with being able to accept connections and process read queries, a hot standby is much like a warm standby, ready to get promoted in case the primary goes down. Now, the primary difference between a hot standby and a warm standby is the ability of the hot standby to accept connections and process read-only queries. Now, as we were prepping for this session, I got a very interesting question from Alex, and he said, why even have a warm standby? What is the requirement of a warm standby when hot standby is, well, it's not more expensive in any way than a warm standby. Why would somebody want something that is used for disaster recovery only and cannot be used for load balancing? I think that it's a very legit point, and it might be a question that comes to mind to others as well. But we've had customers who want to have a hot standby in the same region or in the same availability zone as their primary, but they also want a warm standby in a different region in a different data center or something that is farther away, that does not interfere with the routine operations of the primary database, is just sitting there quietly and receiving those log files without doing anything else. But it is ready to take over, or it is something that we can use to recover from disasters in case it comes down to it. So there's a combination of hot and warm standbys that some customers want, and hence the concept continues to exist.
So Umair, is there any performance benefit to running warm other than hot, or is it purely just to have that certainty that nothing is happening on standby, as it were?
Right. So with the hot standby, remember, we are accepting connections and we are accepting read-only queries, which means that at least some resources of that server are going to be assigned to processing those queries. Now, think of a scenario where there's a lot of log to write on this standby, and there are a lot of queries coming in as well for reading that data. We've got settings in place that balance between whether to apply logs at a higher priority or to service those read requests at a higher priority. Now, in such a scenario, if logs get the higher priority, the read requests will tend to lag and the performance is going to go down over there. In case the read requests take priority, then the writing of the data via the logs is going to lag behind, which is essentially called the replication lag, which means that the standby is going to lag behind the primary. So there is that balancing act that you need to do in case of a hot standby, especially with a lot of load on writing the logs and servicing those read requests. A hot standby could have implications.
Like we lost Umair there. Are you,
Oh,
looks like we lost you there for a moment, Umair. Do you want to just say that last bit again?
okay. Yeah. So I'm not sure what actually got through and what didn't, but essentially, a hot standby has to balance between writing the logs that it is receiving from the primary and servicing the read requests that are coming in. It could be reporting, it could be business intelligence, whatever it is. And in case there is a conflict between the two, there are configuration settings that pick and choose which operation to give more priority to. In case the read requests are given higher priority, the standby is going to lag behind the primary, which is essentially called replication lag. In case the replaying of the log is given higher priority, the read requests are the servicing of the read requests is going to lag behind, and the performance of the read operations is going to go down. So that's the balancing act that you need to do with the hot standby. I hope that makes sense.
Yep. Yeah, that makes sense. It basically, yeah, what you're basically saying is that running hot with the standby, running hot can decrease the performance of actually keeping the standby up to date. So if you have no intention of doing that and you just want it as a final measure switchover option, I guess, it makes sense to run it as warm.
Yep. Yeah. And this is a visual depiction of what a hot standby would look like. So if you see in this diagram on the left over here, the read requests from the application are being serviced by standby number 1, which is a read replica. It's a hot standby. And any, maybe there's a reporting application, maybe there's business intelligence software that the organization wants to use. These requests are being serviced by standby number 2, which is also a read replica. There is load balancing, which means that this primary right here now no longer is servicing any read request. So that load is reduced. It gets balanced out to standby 1 and standby 2. So that is definitely an advantage. You can kind of split out those loads amongst the different nodes within this cluster. Okay. Moving forward. Now, when we talk about replication, we have so far been talking about physical streaming replication, which is the default, but Postgres also provides the functionality of logical replication. And there are some differences between the two types of replication that I'd like to highlight in this slide right here. So physical replication essentially is binary in nature. You replicate the entire database and it gets streamed over to the standby. It is all or nothing. So it's binary that way, as well as binary at the replication level. Logical replication, on the other hand, you can pick and choose. What it does is that it decodes the write-ahead logs, understands what is written, and can selectively replay from the write-ahead logs. So logical replication lets you pick and choose. So you can choose to replicate selected schemas or tables or rows or columns, and logical replication will allow you to do that. Physical replication will not allow you to pick and choose. Physical replication is primarily used for high availability, like the way we've discussed in this presentation so far. It is fast and it is very reliable for high availability and quick failovers if required. Logical replication is slightly slower in performance than physical replication, primarily because there is an extra step of decoding that is involved, but it does give you that additional functionality of picking and choosing what you want to replicate. It even gives you the functionality of replicating between two different major versions. So in case you have your publisher on Postgres version 13, you can replicate that data to Postgres version 16 or 17 or any other version that you want. This is very, very useful in certain situations, especially where you want to do a rolling upgrade of your cluster So you can upgrade one node. It will continue to be a part of the cluster. It will continue to receive those replication changes, and then you can go on to the other node and upgrade it in a rolling fashion. There's one other main difference between the two. In the subscriber for physical replication, you can open it up for read operations, but you cannot have any write operations on it. In a subscriber for logical replication, however, you can write data onto the subscriber as well. Now, this has its own sets of implications, which we'll touch on shortly. Another differentiation between in replication type synchronous and asynchronous replication. You can set, as you set up replication between the nodes of your cluster, you can choose between synchronous or asynchronous replication. Synchronous is when all data is transferred immediately, and the primary node will wait for confirmation from the standby that the standby has received everything that it needs before committing the transaction. So an application writes to the primary node, that data gets written to the write-ahead logs, goes to the vol sender, is received by the vol receiver, gets replayed at the subscriber. The subscriber then sends back an acknowledgement to the publisher saying that, yes, I have received the data, and that is when the application will receive a confirmation from the primary that, yes, your data has been committed. So this kind of replication is critical in situations where data accuracy is critical, where you cannot afford for the entire cluster to get out of sync even for a fraction of a second. There are performance implications, however, because it has to do, the entire data has to do a round trip across the cluster before the application gets confirmation that the data has been committed. There is a performance impact over here, but consistency is guaranteed.
Yeah.
In asynchronous.
No,
Sorry.
please, no. Oh, I was just going to say that again from an Oracle viewpoint. So some of the people on some of the folks on this call might be familiar with Oracle Data Guard, and Oracle Data Guard can also run in synchronous mode. So it's very, this is quite dangerous. It's a great option. It's a very good way of ensuring that your standbys run essentially without data loss, which is fantastic. But this is quite dangerous because what it basically means is that whenever you start to have increased load on your primary, you start to have increased load on your standby and your network. And every single extra transaction per second, creates an extra bit of load on the network and an extra bit of load on the standby, which in turn slows down production, which in turn, et cetera, et cetera. So if you have a big spike in traffic or a big spike in database load, you could really bog down your database. This is the reason why I think it's fair to say, Umair, correct me if I'm wrong. I think it's fair to say that the vast majority of people choose to run replication asynchronously, just because it creates less of a dependency between the primary and standby environments.
That is absolutely correct. And I think that there's one other aspect of synchronous replication that I'd like to point out, and that is in case the replica goes down, the standby goes down for some reason, the primary is going to continue waiting for an acknowledgement from the standby. It will not be able to commit the transaction. So the whole concept of high availability then gets impacted because even though the primary is available and is able to talk to the application, it is unable to commit data because it's waiting for the standby to come back up. So synchronous replication has its own applications and its uses, but there are implications over there. A lot of distributed clusters prefer asynchronous replication primarily for that reason. Now, the flip side of that is that there is a chance that there is some delay in the data being consistently available across all nodes of the cluster because, well, the primary will not wait for any acknowledgement from any of the standbys before it commits the transaction. So the time it takes for the data to travel from the primary to a standby and get committed there, during that time, if you query the same data from the primary and from the standby, you have a chance of getting different results. So there is a chance of inconsistency across nodes for that fraction of a second or that small amount of time where there's replication lag. But overall, the cluster is much faster and it is more scalable as well. And primarily, asynchronous replication is used where performance matters more than the absolute need for data accuracy across the entire cluster. Now, you can also do a mix and match of synchronous and asynchronous replication where one or more standbys are synchronously replicating data and one or more standbys are asynchronously replicating data. Maybe the synchronously replicated nodes are very close to the primary node, and hence, the latency is reduced. And with increased latency, you just opt for asynchronous. So you can do a mix and match as well. It depends on the kind of cluster that you want to design, and it depends on the kind of RTO and RPO you're aiming to achieve. Okay. Now, my favorite topic also tends to be the most challenging, active-active. There's a lot of confusion in
Yes.
in the world where Oracle and Postgres. Yes, Alex is agreeing.
I'm ready to be confused. This is something that because I just want to kind of give a 10-second preface here, because in the Oracle world, this is the idea of having active configurations. Oracle offers some options, some limited options in the form of rack and similar. But anytime you talk to a serious DBA about having multiple active primary instances, I think most folks tend to get a little bit scared. So,
right. And I think this is something that we have experienced as well. Folks that are coming in from the Oracle world, the moment you say active or multi-master, the default go-to technology is rack. And we get asked the question, so what is the equivalent of rack in the Postgres world? Well, the simple answer is that there is no equivalent of rack, but let's understand what we're trying to achieve and see how we achieve something similar in Postgres. So first off, let's be absolutely clear. There is no direct equivalent of rack in the Postgres world. Now, the way that works is rack has a shared everything architecture where you have a single storage and you have multiple nodes that share that storage. And it is at the storage level where the global lock manager exists. And it is that manager that manages the conflict resolution and committing or not committing a particular rolling back a particular transaction. Also, it allows you to have multiple write nodes, and your application could potentially be able to write to any one of them, and hence, it gives you that write scalability across those nodes. Now, in case of Postgres, we don't have a shared everything architecture or a shared storage architecture. That doesn't exist in Postgres. What we do have is bidirectional replication, where you can replicate from the source to the destination and from the destination to the source back. So you have got bidirectional replication, but each of these nodes are a full database server on their own. So they don't share anything. The data is transferred via replication, much like the primary standby architecture that we've seen in the previous slides. The replication is source aware. So the data that goes from from node 1 to node 2, node 2 knows that this data is coming from node 1. And the data that goes from node 2 to node 1 will be aware that this data is coming from node 2. So it is source aware. It doesn't share storage. and it is very loosely coupled. The synchronization between the cluster, between the nodes in a single cluster, is done via logical replication. Now, there are certain advantages and disadvantages to this. A major disadvantage is that conflict resolution is extremely hard. Because storage is not shared, there is no central control of where data is going or coming from. Conflict resolution requires some very special extensions and very special algorithms to implement. And conflict resolution, by the way, is not available in core Postgres. There are some proprietary extensions and tooling where it is available. But the advantage is that you can actually distribute such a cluster globally. You can even geofence such a cluster where, let's say, you have a globally distributed client base, and you want to segregate regions within the database, and you want APAC data to remain in APAC regions, and you want to have EMEA data to remain in EMEA regions, and the Americas to remain in the Americas region. You can geofence in that cluster that is using bidirectional replication. Just to give a bit of a visual feel to this, this is kind of what an active configuration is going to look like with Postgres, right? So you've got these 3 active nodes, 1, 2, and 3. The application is able to talk to each of these 3 nodes. So you've got read and write operations coming here with node 1, with node 2, as well as with node 3. And data is being replicated between the nodes. So data from active 1 goes to active 2, and data from active 2 goes to active 1, as well as to active 3. And active 3 is transferring data to active 2, which then can also replicate that data back to active 1. So all of the data is being replicated, but each of these active nodes have their own storage engine. Each of these active nodes is a complete database server by themselves. Now, the important thing over here is that while this is bidirectional replication implemented over here, this does not resolve any conflicts. So if you've got R1 in active 2 and the same row in active 3, and the application tries to change this row in both of these nodes, there is no way for this replication to determine which change to persist and which change to reject. That conflict resolution is not available in core. So that conflict resolution either needs to be at the application level, so the application is aware that it cannot cause conflicts, or it requires some specialized tooling. We've got tooling like BTR or PGD or PG Edge that's available for implementing such kind of a distributed cluster. Very recently, I think this is less than a month ago, Amazon actually open sourced what they call PG Active, which is another extension that handles active configuration with conflict resolution. So that is another player in the mix that's now coming in.
So, Umair, just before you carry on, because we're getting a lot of questions coming through, by the way, which is great. Keep sending them, folks. I mean, a lot. I'm starting to get a few similarities. So quite a few folks are asking around about, look, basically, how do we resolve data consistency if you've got, in this active configuration? Now, I know you've literally just talked about it now, but can we maybe just so folks can leave with a soundbite, as it were? Can you try and just summarize it very concisely? Let's assume you've got an active configuration of some kind, not using shared storage, all right? Let's leave out all the details. Fundamentally, how do you avoid data conflicts?
Right. So in this particular case, if you look at the diagram that's in front of you right now, in order to make sure using open source Postgres that no conflict exists between, between active 1, active 2, and active 3. What you need to ensure is that the application is conflict aware. Let's assume that active 1 has data from the Americas, active 2 has data from EMEA, and active 3 has data from APAC. So any changes in the APAC data, while they get replicated to active 2 as well, will not conflict to any changes in active 2 because, well, the application is only making changes to the EMEA data in active 2. And they, in turn, will not conflict with active 1 because the application is making only changes to data of the Americas in active 1. So that is conflict resolution or conflict avoidance at the application level that you can do with open source Postgres.
So how would you go about setting that up? Is that something that has to be configured within the application with regards to, you know, making the application aware of which node it's using, or is that something that can be configured within Postgres itself based on the structure of the database?
This will be outside of Postgres. So this will be at the application level. This will be application that is configured to make sure that it is aware which node it needs to write to. So for the folks on the call, and we'll wait for Alex to hop back on to be able to correct me if I understood this question incorrectly. Essentially, if you want to use open source Postgres and use logical replication that is available in core, and you want an active cluster, this diagram right here in front of you, this will help you achieve that, but it will not resolve any conflicts in the data. So such a cluster needs to be designed in a way where the conflict resolution or conflict awareness comes at the application level. So the application needs to know which node to write to. However, there are some proprietary and some very serious production grade extensions that are available to Postgres, using which you can implement conflict resolution methodologies like CAMO, which stands for commit at most once, or last update wins. And there are also conflict-free replication data types that are implemented that you can use for such an environment. But that is available outside of Postgres core. So I hope that this answers the queries that we were getting. I'm not looking at the questions, and we'll wait for Alex to come back in and see if some of these questions have not been answered or resolved by this by this response of mine. But I'm going to go ahead to the next slide, and we'll come back to this if there's more stuff to cover. Okay, now high availability tools, because implementing this entire cluster and replication and high availability, this can become very, very complicated. And I tend to be a very big fan of automation to the extent possible. Human intervention can cause human errors. And for database clusters that are mission critical, that cannot afford to go down, or where mistakes cannot be tolerated, automating is the way to go. So there is recommended tooling to set up these clusters and replication in Postgres. The very first one in this list right here is Standby MP from DBvisit, a very simple to use tool that automates the setup of an entire cluster with Oracle as well as Postgres. It is visual in nature. It has a very nice GUI that you can just point and click and set up the entire cluster. Petroni is one of the more popular tools that are out there in the Postgres world. It implements the entire cluster as well as auto-failover solution. So you can design your cluster with replication and auto-failover using Petroni. And how it does it is that it does a consensus-based mechanism which is why 3 nodes are required. You always need to have an odd number of nodes in order to have one clear winner. It does a distributed consensus, and it integrates with etcd for leader selection. And the last tool in this list is pgpool2. It not only implements clustering, replication, and failover, it also implements connection pooling and load balancing. So when we looked at that 3-node cluster where you can write to the primary and read from the standbys, pgpool will help you implement that in an automated fashion. And it also has automated failover. And we have a tool by the name of pgcirrus that is designed and distributed by Stormatics that creates a wrapper around pgpool to help simplify the setup of a Postgres cluster using pgpool2.
Sorry, I dropped out there, Umair. It's the network. It always, network always fails when you least expect, right? Weren't we just talking about the replication? Well, this is exactly what happens.
Exactly. Yeah.
Yeah.
Exactly. So yeah, network can be a little challenging, and you want to make sure that you are, you have redundancy in place, and that is why we have 3 people right here who can
That's
take
right,
over in case one of us drops out.
And that's why I've just switched over to using a mobile connection. You see, I know how this works.
Yeah, backups are absolutely critical, right, in every aspect. So some of these concepts that we have, discussed so far, I tried to, based on my limited knowledge of the Oracle world, I've tried to kind of map what it means, what equivalents we have in the Postgres world. So data guard, which is typically physical standby, an approximation is the physical streaming replication that Postgres has. The active data guard, that would be like the hot standby that we discussed, where we have a read replica. The data guard broker, the approximation is Petroni, where you have an automated failover mechanism implemented. You implement the cluster and you can failover automatically. RAC, I'd mentioned, we don't have an exact equivalent of RAC in the Postgres world, but you can implement something similar for high availability and active-active configuration using logical replication. And again, using that same logical replication, you can implement Golden Gate type of functionality. So these are the rough equivalents if you want to map concepts from the Oracle world, high availability of the Oracle world to high availability in Postgres. And well, this is the second last slide. Here's a QR code. We're actually running a 1-day intensive training on Postgres that's designed for Oracle DBAs. This is taking place exactly a week from today. If you are interested in attending this training, just scan this QR code and register. It is going to be led by one of our experts who has dipped his toes a little bit in the Oracle world as well as the Postgres world, so understands. And it will be a full day hands-on and instructor-led. And that brings us to the end of the slide deck. This QR code is my LinkedIn. I'm happy to connect with anybody who wants to connect, and I tend to be active on LinkedIn and answer queries as well. My X handle is PG_Umair, and I am happy to take any questions.
I think I'm still here.
Yeah, you were just cutting out a little bit, Alex, but we've got a few questions that actually we've got quite a lot. I'm not sure which ones have been answered already. I'll just go ahead and read out one that I can see here. Do we have any sort of service using which we can enforce that APAC service, Europe service, or America service writing on their preferred node, and behind this schema it's replicated? Apologies. If hopefully I said that correctly. I was just reading the question. Umair, are you able to answer that one?
So what I understood from what I heard is that if there's some kind of a service that can be used to ensure that data from these different regions that we talked about doesn't overlap or interfere with each other. Yes, you can implement geofencing. You can ensure that even within a single cluster, only selected data gets replicated to different parts of the cluster. So APAC data does not get replicated into the EMEA region, or EMEA data does not get replicated into the Americas region. You can enforce that by using selective replication. I hope that is what was asked.
All right, there is another one.
Unfortunately, for some reason, since I've reconnected, I actually can't see the questions and answers anymore.
That's all right. I can read them out, Alex. No worries at all.
Blank
There
screen.
is another one which says also, if I'm not sure if this is a question or not. Also, it would mean committing to that space on all 3 active nodes in order to have a data in all the same nodes.
So I'm going to assume that the question is about those same 3 regions. We're talking about Americas, EMEA, and APAC. And the question is if the data will need to be committed on all 3 nodes. Well, if you want the data to be available across the entire cluster, across all 3 nodes, you don't necessarily have to commit to every one. The data will get replicated. If you want the data to be there, you can replicate it across the node. So let's say the APAC region commits to the APAC node. That data, if set up correctly, will replicate to the Americas node as well as the EMEA node. So you don't have to commit separately. I hope that I understood the question correctly.
I think you got it right. Perfect. And we've got another question. Is there a set of monitoring tools that help visualize this data flow when setting up and running replication, including health and what the delays are?
Yeah,
I'll take this one, Umair.
Sure.
So this is the absolutely perfect use case for our tool. So DBAs standby multi-platform is based around a real-time dashboard that gives you very, very clear visibility on exactly what you just asked. You can immediately see where the replication is, what time gaps are, what any problems, if any. As well as set up easy notifications going to email or Slack to make sure that you respond on time. So yeah, do check out DB Visits P if you're having these issues.
All right, I understand we are 1 minute over time. Apologies, everyone. If you do have time to stay on to ask some questions, please feel free. If you have to jump off and you miss some parts of the webinar, we will also send the webinar recording. There are a couple more questions, Umair and Alex. So like Oracle ASM, where does Postgres data get stored in?
So Postgres data essentially is stored in write-ahead logs. And that is where the commit comes from. That is where the data persists. If my understanding is correct about ASM, we don't have an exact replica of ASM in Postgres. The data persists on disk, and it uses write-ahead logs for that persistence. This is beyond the scope of this particular session, however, because we are talking about high availability. But I'm happy to take this offline in more detail if that's required.
All right, I think there was another question. I think we'll just go ahead and answer one more question.
Yeah, maybe one more, Aaron.
Yeah. Is there an active solution in Postgres? For example, in MySQL, there is a Galera cluster that allows us to read and write on all participated cluster nodes.
Right. So in the Postgres world, because this is open source and this is an entire ecosystem built around the database engine, there are multiple options. Some of them are proprietary in nature. A couple are open source or source available. So I'm just going to say out a few solutions that are available for active clusters that include conflict resolution. First of all, we've got PGD, which stands for Postgres Distributed. This is a proprietary extension to Postgres that is distributed by EDB. EDB is an organization, it's a pure play Postgres organization that has been working in the Postgres ecosystem for more than 2 decades now. Secondly, there is a newer entrant by the name of PG Edge. They offer something very similar to PGD. Again, it's a globally distributed active clustering of Postgres that they offer. Their use case is fine-tuned for edge devices and IoT that are distributed. So that's a second option. The third option has very recently been made open source by Amazon AWS, and it is called PG Active. Again, it is an active configuration for Postgres, handling the cluster and the replication between the active clusters, including conflict resolution. But it's something that is very new, and I'm not aware of a production deployment or critical production usage of that extension, not yet, however, at least. It will probably mature over time and become a good third option. So yes, to answer that very, to summarize that answer, yes, pooling is available in the Postgres world for active clusters with conflict resolution.
I think we'll leave it there, Umair. Thank you, folks, for joining us. It's always good when people have lots of questions, isn't it? It means it means that we're talking about something relevant.
Absolutely.
Yeah. So thank you very much, Umair. It's great to have you do these sessions with us because we're coming at this from the Oracle space. You're coming from the Postgres space, and together we make something beautiful. So thank you, folks, for attending. I hope we'll talk to you again real soon.
Thanks, everyone. Take care.